Welcome again to another Kent seminar lecture. Today, we have Professor Linbing Wang with us, and I'm gonna give a short bio of him, and I'll hand the microphone to Professor Alcari if he wants to say some words. So let me go through it. So Dr. Linbing Wang got his master's and PhD in civil engineering from the Georgia Institute of Technology. He also has a master's in geotechnical engineering from Tongji University and a bachelor's in hydraulic engineering from Hohai University. He is currently a professor and the director for the Sensing and Perception Lab and the Safe and Green Mobility Living Lab at the University of Georgia. He is the founding chair of the Committee on Mechanics of Pavements, former chair of the Nanomechanics and Micromechanics Committee, a fellow of ASE and EMI, and Dr. Wang's research interests include multi-scale characterization, modeling and simulation, material genome and performance predictions, sensor and IoT sensor network for structural health monitoring and safety. We are very proud to host Professor Wang here at ICT. Let's give him a warm welcome and Professor Wang.
Put me on the spot. All right. First, I definitely would like to welcome a very, very dear friend, Linbing Wang. I've known him for so many years, and definitely we have a very special guest today. First, I would like to talk about his outstanding intellectual and scholarly work. This is always very impressive. But also I'm talking about his personal aspect. He's one of the most ethical and moral people with high morals that I have ever met. Linbing, we're very, very pleased to have you with us here. And one of the good points in my life is when visiting with Linbing and show me around in China, my first visits there. So I'm very, very glad to have a dear friend with us here today. Thank you for coming.
Thank you. Okay, now here and this one is here. Thank you, Ima, for your kind introduction, and I really love this introduction. Ima and me, we are similar age, but by academic, he is my advisor level. Academic much earlier than me, and I worked in the industry for many years. It's like he just introduced me about my bachelor degree in hydraulic engineering and my geotechnical master is in geotechnical and practice engineering for almost 10 years and joining the academia 2000 at LSU, and then you move to Virginia Tech at Ima's recommendation. So I took his office, right, at Virginia Tech, and often receive an email or receive a call. And I talked to Ima, and yes, I'm his friend, and he moved to University of Illinois. And sometimes there are people calling in, speaking in Arabic. Right? And I know this must be Ima's friend. So we shared a lot, and I really fully respect so much, of Ima, his highly morality and leadership. I really appreciate that a lot. And always follow as an example. I'm speaking from my heart. I don't care about we are the same age, almost. I am 1 year, younger than Ima. So he is my elder brother. Right? He's always bigger than right. So this is my second panel lecture. Panel. The first one is 2016, and the topic is related. After 8 years, I promise you, I'm going to continue working in that area. And today, I will report that area. Right? It's data-driven approach. Last time I talked about one is just a model scale modeling, the rational mechanics. The nanomechanics, asphalt mechanics. That's the work that I've been working for many years, and this past 5 years, I shift that one into this area, but it's not I shift my focus, but it's the work. Dr. Jing Liu and Dr. Fang Liu, they did the work, right? So in the last 5 years on this. Yeah. This is a brief outline. I'm gonna have to six topics, related. It's one is the data-driven, strategies, for general materials discovery and design. And the second one is the current asphalt mix design challenges. What are these challenges? The third one is machine deep learning and data processing approaches. And the fourth is the data sets for this research. And number 5 is the mixture properties, performance prediction, and distress quantification. It's based on AR approach. Right? The last time we talked about all this rational mechanics, multi-scale modeling from molecular dynamics, macro mechanics, and FEM, DM modeling simulation last time. And today we talk about the data-driven approach. It's promising for 8 years. Right? After 8 years, we really made a progress. And this is the first talk I gave and prepared a special for this, Handle lecture. First time we did a lot of work, but I never presented it. But this time I presented it over here. And the number 6 is the data-driven approaches for accelerated asphalt computer mix design. First part. So it's a general, this is the history. Look at our entire history. Material design is very important. Finding materials is very, very important to the entire human society, right? We classify our, categorize or classify our civilization according to the materials, right? It's very important. And you look at this history, the brief history over here, and from the alchemy, right? You probably heard about that. Try to making gold, right, out of this soil. Right? That's a dream, and so we like it. And materials genome, 2011. And that's the time, this material genome was initiated. And I think it's 2010, 2011. Yeah. So the talk that I'm giving, 2016, it's on rational mechanics. And here you see this one, right? The difference, the difference between, the traditional mixed design or material design and the genome-based design, the 2 columns. One is data-driven, another is rational mechanics. Traditional experimental, right? Experimental method, and they added these 2 additional columns. So last time I talked 1 column, rational mechanics, modeling simulation, and today data-driven approach. And I chatted with Angela and Dr. Fang Liu, right, this morning during lunch and time, during breakfast time. So the next would be them to talk about this, about the integration of the data-driven approach and the rational mechanics, right? Both of them integrated with with the experimental, right? Data-driven approach is related with approach. Rational is also related with the experimental part, right? So they have a lot of research going on in this area, right? It's typically what they do is this material property, right? Prediction using this data-driven approach, and metal materials automatically screening what type of materials satisfy your needs, and then metal material property oriented design and optimization, right? So you come up with a kind of drafted design, how can you optimize that? It's data-driven approach. They have a lot of progress in this area, and in our area, relatively behind, right? And in the crystalline, type of materials, focus on 2, major areas. One is highest throughput virtual screening. Right? What type of materials can satisfy your needs? Right? It's just a virtual screening of many materials from all possible combinations. Just with data science or the data-driven approach, you are able to do that. You cannot perform so many tests, right? That's a last a long time and it costs a lot as well. And then another one is the inverse design. Design material by desired problem. Right? That's our target as well for asphalt concrete mixed design. So your target is particularized, rotting at international, all this, you have design properties, and then I'm gonna come up with a design that satisfies your needs, right? And currently it's not, currently it's just empirical, right? It's an empirical approach, right? So we can talk about this, this area. It's the balanced mix design, right? We talk about this, V mix design, we talk about, marshal mix design, supreme mix design, and more recent years, it's just balanced mix design, right? Try to come up with, the properties of different, performance, and they come up with, same kind of performance period time. And various, approach like volumetric design with performance verification, that's volumetric design with performance optimization and performance, modified volumetric design, and then performance design. So our goal is going to this performance design. It just you have such kind of desired properties. How are we going to design the mixes? Right. The disadvantage of the current approach, even all this, just based on the testing. You come up with a volumetric design, and then you're using testing to verify or use different tests to evaluate this performance. And a tremendous amount of data that being in the history was not taken into consideration, right? So that is something we needed to make use of this historical data with the data-driven technologies in recent years to leverage this existing resources. So this is very familiar, much stronger than me in this area. You have a lot of testing methodology, and you perform the testing. It's typically like a mixed design, at least 7.5 working days, right? More than a week, roughly 10 days together, right? And a lot of testing, a lot of materials consumed, and plus you typically have only 1 or 2 tests, a hamburger testing, right? Or even an APA, a full-scale testing. That testing evaluate only 1 or few testing, parameters in there. The criteria may not be just to cater all the needs, all the desired properties, right? You cannot evaluate all the properties. That will cost much more, right? Like many of the state DOTs, they have like either fatigue, or rotting, right? It's true, imagine, performance parameters, but in the National Roughness Index, and the other properties must be considered as well. And the traditional approach would not be able, or not easy to address this problem, right? So there's 2 major challenges: time and funding consuming, right? And another one, your choice may not be an optimal choice, or that your choice may not need so much money or so much time to come up with. Historical data may give you a solution already, right? So this is the one that we wanted to do. That's our motivation for doing this, right? It's our motivation over here. Tremendous amount of data at the farm, the entire process. Raw material preparation, right? And the manufacturing this material is paving, all this process, the data will give you some of kind of like a link to the optimal, mix design in there. Right? We have to leverage all this existing data, and the process in there, and use this one for our pavement design, for performance prediction, and so on, so forth. Right? So for that purpose, we come up with quite a lot of individual models. This is all the AR, or deep learning, machine learning based type of models for like a volumetric property prediction, rotting, cracks, international roughness, and other mechanical properties, dynamic models. We come up with all this type of individual models. And through this optimization, different procedures for optimization in the AR category, like the gray wolf optimizer, and so on and so forth. Many of them, Jinliu and Fang Yu, they did an excellent job. They, within this roughly less than 4 years, I remember, right? Less than 4 years, they tried so many different approaches and identify which one would perform better, right? And use that one as recommended procedure, right? And then with this together, then you can recommend the mixture volumetric property VMA, for example, mixture gradation, right? And other mixture properties, and then find the performance. So this is the entire system that only two of them, right? Mainly, Jing and Fang, the two of them, they did this. So I'm so proud of them, trust them. And plus, they are all here. Jing is also online. So they did the work. I am doing the presentation on behalf of them. But the honor should go back to them, right? That's it. So machine and deep learning and data, processing approaches, right? And I remember, 2017, I developed a new graduate course. It's called sensing and deep learning, right? Just talking about all sorts of deep learning approaches. But I didn't use them a lot. And so many years, I look at it, oh yeah, I remember something, but I forgot the detail, right? So if any detail, then maybe Jingyu and Fang Yu can answer these questions. So we used a lot of this, approaches, right? Approaches that we use and to process the data and come up with the models, and some of them good, some of them not so good, right? And those are the ones that we use, like support vector regression, neural networks, regression, decision tree regression, and auto regression, integrated moving average, and this, different type of posting approach and Gaussian process regression as well. These are the approaches that we tried. We tried on the different sets of data, and also other ones like including over here is just recurrent neural networks, non-short-term memory network, and generative adversarial networks, and convolutional neural networks. And in this one, we specifically after comparison of there's so many different approaches, we selected 4 types of networks for this application. And graphical neural networks in there. So these young people, they do this so quickly, right? It's within this 3 years, and I strongly believe like Fang Yu is a very good expert on this LSTM, right? For that study, memory, he did a lot of modeling about the mouse, neuroscience, and we got a project on the neuroscience. So he did a lot of work on that. His support from but his dissertation is on the materials. Right? So did a lot of work, but not included in his dissertation. And data processing and future engineering techniques, we have a lot of outline identification specific in the code density estimation, Bayesian data imputation, and dimensionality reduction. It's just a principal component analysis, right? And the dimensionality reduction autoencoder, recursive filtering elimination, and biasing. All these technologies should be tried in this application and identify the best performance. The performance we use is these parameters, right? These parameters is mainly the errors and R squared and sum squares. And this one is also for the optimal, multiple objective, optimization. We use this high volume indicator. Very good job. I think they did an excellent job. I strongly believe. I love what they have done. And this one, the generative adversarial networks, we use data augmentation, right? This is also a very typical approach that can be used in the data science section. And this is basically for the time series. Then we apply this AI approach to model the future performance of the pavements and materials as well. This is the aroma and recurrent neural networks and non-short term and gated recurrent units. Right? This all these approaches are being used for time sequence modeling and simulations. Right. So this is the approaches we have used, and others here is a temporary graphical neural network as well. It's talking about the relationships of different type of performance indicators, like rotting, fatigue, cracking. They are correlated as well, right? We understand that, and how we can use this one to identify the importance or the cross correlation of these different parameters in here. Okay, this And also this non-dominating or sorting algorithm, right? This sometimes it's a very difficult to make a judgment, right? It's not a dominating kind of factor, and how you can make a decision under this type of situation. They have this approach to identify. And a green wolf optimizer, right? The iteration process, and then to come up with the best solutions, especially for the balanced mixed design. Balance means so many parameters, so many kind of indicators, performance indicators you have to optimize overall, right? So that's a very challenging or complex, kind of data approach, data science approach. And this is two, basically architectures that we developed, for this image, identification, cracking identification, and specific architectures. Of course, there are a lot of architectures, in the development here. For each of these, basically, distresses, we have different architectures in it, right? It's no free lunch, right? You cannot have one architecture to be applicable to all of them. Yeah. So that's the second part. I said the third part of it, this fourth part. Talk about the data sets for this research, right? Data sets. The first, data set, the LTPP, I'm so lucky, my second project, when a big project, when I come to the United States, is the LTPP project. That time I'm working with a company, and then the law engineering, and we did a lot of material testing for the LTP project. And we selected a lot of features, right, important features, and through this various type of data processing, quality control, and so on and so forth, right? Outline, removers, and so on. Finally, we come from with this, from 36, to 27, types of features for this, predicting watching this data of LTPD. And from the data set for the predicting allocator cracking, right, and then longitudinal cracking, this, we have the features, through this analysis, this the criteria that we use, right? We use develop this, criteria we use, and from 45 drop to 33, right? Sometimes that's a dimension reduction, reduction process. And imports, several categories of imports, in here is the pavement structural, material properties, environmental properties, and mixture, volumetric properties, subgrade and surface, various properties that come from the LGPD projects, and the output of the rotting, cracking. Right? That's the one that we try to predict in there, or to design to establish a correlation or relationship between this, imports and the output, right? The performance, right? It's multiple variables in. And another data offset is a real project. It was a research institute of highway. You might remember, so I mentioned to them I had a very nice picture, but I don't know. Did I share the picture with you? Remember that night after this one, we went to Tiananmen Square as well, right? Yeah. We took some, very nice picture as well. And this is a testing track that have 38 pavement sections, structures, and then 19 of them are asphalt concrete. And this is being continuously monitored. Now I think it's already like more than maybe 30 billion, 30 million kind of issues already. It's a lot, loading in there. So we got this data from Xudong Wang, right? A common friend of mine, so this is another data set for this, study, and this is basically the infrared imaging, Fangyu acquired. Now, the first idea that time I went to VTRC. When I was interviewing, I put the infrared imaging as an option. The infrared image comparing to the optical image, there is a tremendous advantage. The most important advantage is this thermal conductivity. thermal, transport is well-established theory, right? Related with materials and temperature efficient process. And that process is directly linked to the depth of the cracking, right? Through that, kind of energy dissipation or the temperature dissipation process, if you continuous monitoring for several periods of time, will give you tremendous of information, more information than optical imaging. That's a very good advantage. And one of the researchers in there, they don't want to support this one. But after maybe 14 or some years later, they started doing this research by themselves. That's how it's interesting. I say this is something I have the infrared imaging and I can we do that. But after 14 years, I remember it's 14 years they started doing the infrared imaging. And it's through this fishing imaging to probably better quantify the cracking, characterize the cracking and other material problems. And especially, for the infrared image, you can apply image during the night, right? During different time, not just under good sunshine, but it can apply images at different times. So the next one is the mixture properties and performance prediction and distress quantification. And I receive basically instruction, so I should better just limit my presentation to 35 minutes and then leave more time for discussion, right? I'll try to follow that, recommendation. Maybe a few more minutes, right? Oh, okay. So this is the results. Remember, we talked about the different approaches, right? Data sets and so on and so forth, and then we'll come to the result of the prediction of this one, right? So this is the first one is watering prediction. Watering prediction, we have this linear regression, the traditional approach, regression approach, right? This is the results, it's a comparison, right? The comparison, and the one that we use is the gradient boosted approach and artificial neural network, right? And then you see these results pretty, reasonably good, pretty good. And if you're using, the traditional linear regression, you'll come up with a poor regression. Right? And this is another one. It's another study. The particular was, measured values of rotting, on the imputation, data set, right? Remember we talked about the imputation of the data. And you also come up with a very nice, correlation, very nice. But of course, always the data, science approach using the big data is always better because the function basis is different, right? So you're running the traditional regression analysis, you use x linear or x square or log, you found a limited selection of this basis function. But with the data approach, through this, so many kind of combinations, you come up with a very good estimation of all sorts of non-linearity. That is the reason. That's the most important reason that why data science or big data approach give you a better, relationship, right? You see, that's always so trust that because that is a mathematical that you can prove that it give you a better solution. It's in. And then this is the solution. The kind of conclusion. The gradient boosting model has the best performance, in this one, right? And it's all ML models, they perform better than the traditional linear regression or regression based on some of its functions, right? Select the function, for example, log function, right? You see that many of these functions have log function in there, right? It's selected or square and so on, suppose. But this one, the linear approach, the data approach can accommodate all of them, right? It's just by data in it. And this is the prediction from the real tracker data, right? This real tracker data, various approach for the prediction of this, rotting depths, rotting depths, and this rotting, various approach, right? So, and this, I guess, this probably the best, give you the best performance. The R square is 9.949, 0.95, so reasonable nice thing. And rotting prediction using deep learning for time series, right? This time series, and we have several approaches that there's 3 approaches are being used. Right? use that, and then, it's one, the time series specs are many to one architecture, many, to one, performance, indicator and time sequence, and many to many, right? Just remember, we have several, types of, distresses, rotting, fatigue cracking, and, this is, the approach that we developed, two types of approaches for this. And, these are the results for the rotting prediction. Rotting prediction, and then you can see that, this is the color, right? This is the, K-mean clustering, right? This is approach, gadget recurrent unit approach. This gives you the best results with experimental with combination measurements in it. And this international reference index, prediction, this using this graphical, basically the graphical input in there, right? And the relationship between these various type of distresses. Remember, international reference index is not a simple measurement. That measurement is related with rotting or related with fatigue cracking and the initial international reference index as well, or the construction conditions in there, right? So this is why we use this approach. The others we use simple ones, but for this one, we use this graphical neural networks. And this is the kind of matrix between different parameters of the transfer functions as well. And here is the prediction results. And this R square here is pretty nice. It's the GPI approach, approach over here. This autoencoder GPI, and it's density, density function over here, and the basically combined, right? This is a particular actual measurement by GP and AE the GP approach, autoencoder, right? And the conclusion is the combination of AE, autoencoder and the model can improve the performance, especially the GPR approach, which implies this is a better one, a better approach for this. And cracking, right? Alligator cracking and longitudinal cracking. This is remember this is based on the LTP data. The LTP data, we understand that the weighted equation or whatever, right? It's a fatigue cracking, and of course this DI is a very good, very complex function of various parameters in there. And we use the basically the AR approach for this, right? It's principal component analysis annual ANN, this the neural networking in there. And this is the prediction results, right? This is a kind of transfer functions from this type of like a regulation. You come up with this R square is almost equal to 0, right? Essentially, there is no correlation. We understand, right? Because there are so many parameters, and then it's how to say the space, the function space is very much limited with this type of format. And for this one, and then we got this much better one, right? 0.839, and this is a 0.87. So using this AR approach indeed improve this correlation or the modeling and the simulation actually. And the next one is just talking about the basically quantification of this cracking severity classification, right? Using this longitudinal transverse cracking severity, and this is some kind of like a judgment or the people's like a trend set, right? Just people judgments. This is a low cracking and high, intensity cracking and so on and so forth, and compare that one with our machine classification or categorization approaches. And this is basically the results, right? Different type of results in there, in here, and compare that one with our human judgment. The group, finding and several students can be trained to classify this type of image and compare our own image classification with the machine classifiers. And this is also the results by of different times, morning and noon and some different times, you know, we get this results and make the fishing image, the infrared image and optic image, and fuse them together and to come up with a judgment. And we discovered that as fishing images typically give you better results. Prediction results are relatively better. Okay, so that's the results for the distresses and the results for the other properties, you know, like rotting and fatigue cracking. And now we talk about the modulus, the dynamic modulus, right? So one is this one is also a weight cycle equation, right? So some of the comparisons that one. And the one that we did is basically, you know, using this, you know, total vector, you know, approach and, you know, efficient neural network approach. And we come up with a very nice prediction. The prediction results are much better than, you know, the weight cycle equation. And this is a plot of this, you know, results against this basically this is type of like a the standard deviation or correlation efficiency in there, right? So we come up with this kind of plot in there, and so the lower part, right? This lower part is indicating that, you know, this is the prediction and the actual results, they are more basically consistent with each other, right? And then the other part would be not, right? So this and this is also indicating that, you know, this machine learning and auto-encoded machine learning models will give you a much better result. And this is so many different methods that I have tried many methods. I'm not able to go into the details, and they, you know, Jing and they have a much better, you know, understanding of this, how this, you know, performance and how this models perform. And then later on, you know, later on we also did a work basically using, you know, the dynamic modulus, you know, come up, you know, the predictor using this machine learning models, right, from the visual properties and the temperature and so on and so forth, and this type of properties, and then predict this, you know, modulus, dynamic modulus, and use that predicted dynamic modulus for the payment design. I strongly believe this is something we needed to leverage because, you know, DOTs, they have performed a lot of testing. You know, if we can collect this data and come up with, you know, kind of calibrated models, right? Use the machine learning models, and then different DOT, you know, they have the specific data in there. We may just calibrate this, you know, machine learning models, and then use these models to do the prediction. Because that recalibration is much easier than, you know, the traditional MEPDG calibration, right? The model, you know, take years, and many state DOTs still didn't achieve that. So these are the results, you know, generating, you know, grocery networks, you know, for data augmentation, right? This is after that one, we do this, you know, partial dependency analysis, and in a sense, the parametric study of various type of like parameters, how they are contributing to each other and to the performance. Right? Okay, so that's the part 5, and now it's the last part. Maybe a few minutes, you know, over. Right? Data-driven approaches for accelerating asphalt mix design. Right? And here, most of you are very, you know, strong expert in this area, right? So the mix design, you determine the gradation and optimal asphalt binder content. And with, you know, the historical data, the machine learning approach can achieve that much more convenient, right? And essentially, we discovered that if we use, you know, the effective asphalt binder as the design parameter, it will give you much better results. And this conclusion, you may have that even without this, you know, result, right? Because it is effective asphalt binder content that plays a major role for performance, right? A soft asphalt binder content will not play a role, right, in there. So that's a good, you know, approach in there. And we indeed, you know, discovered that's true, right? It's true, you know, in there. And I think this is a major, you know, effective, right? Majorly effective and predicted effective. And if you use, you know, this, machine learning approach, this give you much better results, right? You can see this, right? 0.8, 0.9, 0.7, 0.8, right? It's just, give you a better prediction in there. And, of course, you can have this, effective and observe, this both, have a prediction, right? In there, and it's also give you a better results. So my recommendation, for future, design, we should design for the effective estimate by content, not the total, right? And this is the optimal design for, multiple, green wolf, optimizer, right, machine learning methods. And this is the kind of controlling equations, right, the controlling points, percentage, and so on and so forth. This constraints, some of these constraints in there. And we even, poke this is basically the CO2 emission into this consideration, right? Consideration is a multiple object, optimization process. They come up with a design that are not only satisfy, the performance, but also satisfy some of the requirements for the minimizing of the CO2 emission as well, right? So that's this, green asphalt mix design. So this paper was accepted, by TRB this year, right? And we also, I think, Jim, from you also on that disorder, we got this LTPP, two LTPP, data analytical second place, right? 2 times, Jim, you and Fang Yu also did it. Just this is optimization using multiple variables in there, right? So I guess this is the framework after this one, right? We come up with this framework for this design incorporates data approach, right? Data approach and just yes, it's sufficient particular models, data sets collection, whatever, if you can apply this one to university, to Illinois DOT or the Michigan DOT, you probably can come up with some of data from there, and that data set may be even better, right? Be more unique, to the application, and then you have this various type of like requirements, raw aggregates, properties and in there, and just import this one into your basically objectives, right? This objective you're going to define for your mixed design, and then the system. So this entire system, various modules that we developed, then you can optimize that design to come with the recommended design. Output is just a right proportion, of aggregates as per the content and so on and so forth, right? You agree? So that's a newly, design framework that incorporates the data analytics. And in the field, you could incorporate this mechanics analysis together, right? And truly to achieve that material genome type of mixed design objectives. This is actually this is in a sense, from all this information can come up with this optimization process, right? Let's do one example. Right? This is just one example design is 12.5 nominal maximum aggregate size and 19, right? This to using the volumetric design and balanced mixed design, right? And these are the results. The results come from, I'm not even go to the details, and the one is going to the right. So, yeah, this is the in a sense it's basically conclusion of this one. This conclusion using this AR based mixed design got some kind of results pretty consistent with our traditional understanding. Understanding like this mixture and the force mixture lower rotting rate, and this practice increases cost decreases and so on and so forth. Right? This is in a sense to give you a general trend that is consistent to your traditional understanding. Okay. This is the results. This is the final results of this one, right? So, but the specific details may not make a lot of sense. Oh no, it makes sense, but it's not so important to a certain degree. But the general trend is important, right? This approach gives you all the results that meet the rational understanding of your material design. Okay. So 45 minutes, still have 15 minutes for discussion. I'd really love to discuss with you. And if I saw a big challenge question, I will address that one to Jenu and Fang Yu. Most of them are Jane online and Fang is here. But I will try my best to do it.
Thank you for the great presentation, Professor. I wanted to get your opinions on how would you implement this intelligent balance mix design from a DoT perspective? Because I'm gonna assume that it will certainly cause a change between the liabilities that might be with the contractor when they're making the mix according to this framework. Compared to what they have now, basically. Like I don't know what direction this might go in, and I wanted to see what your opinions might be.
Yeah, okay, that's a very good question, This one would not basically have any kind of conflicting with, your existing knowledge, right? The best advantage for this one is leveraging existing data. This data is in there, historical data is in there. But in our current situation, most of the DOT, like a current engineer, he may not, be able to review all this kind of previous data, right? To come up with a very good mix design. But now with this approach, this module is already there, and you see LTPP data is already, LTPP data is different states, right? Pretty representative. And if you add, some additional data from your state, like we do the calibration of the MEPDG methodology, right? So that local data would give you more weights. And use that data and use our LTPP data for this approach. This is type of models, various models, right? We can come up with a better screening or a good recommendation of this draft mix design, right? The draft mix design maybe achieve multiple objective optimization instead of one or two, right? So that's the advantage I could envision. So it's just easier for them to adopt because this models are relatively easier to implement, right? The most challenging part is just collecting the data because the data from DOT, they forgot. They don't know where the data anymore, right? So historically, like, the data, so many mixes, designs, they may have only a few recorded and they don't want to share with each other sometimes, right? So that's the challenging part. Implementation wise, I really don't foresee any kind of like a conflicting with, the contractors, right? Because this methodology just give you a better optimized mix design. I think they should welcome that. That's what I understood. Right? They should welcome this, and it needs to give them a certain opinion, the machine opinion, right? Based on the historical data. You agree?
Thank you.
That's all. Yeah.
Thank you, Professor, and very neat slides and interesting presentation. I am building up on his question, and I just wonder the data that was used for training the model. I understand it was like the LTPP sections, which were considerably old compared to type of mixes that we have nowadays, type of additives, type of new materials that are being used to new roads. So I wonder how this framework would be more flexible to fit these new mixes and the change that happened since LTTP.
Excellent question. Excellent question. I understand your question. Let me repeat your question. You ask basically, this is a kind of new, maybe in the past, maybe 10 years or past 2 decades, we have a lot of new mix designs, right? New materials, implemented. And this data, OTPP data is just relatively old one. How are we gonna update this one, right? I take this question to Imam. You know why I take this question to Imam? Because he potentially may be able to do something as a leadership. And I don't think I'm able to achieve that. but I definitely can assist you on this, all right? So I think it's probably, maybe a next, LTPP, small scale, right? LTPP project. And today it's much easier to handle. Historically, LTPP project collect data many manpower, right? Cost a lot. And today we can use these sensors, various type of sensing, remote sensing, all this kind of data collection more easily, right? More conveniently. So we can add this data, collect the new data, right? Add them to this database, or we establish a separate database, recalibrate these models, right? That could be, but with this type of, you can say, this is basically, many genius work and Fang's work. It's just 1 or 2 PhD students, right? You agree? And with this data, by collecting data, it takes a long time. LTPP, $50 million, right? And then now the one, I think maybe just we focus on several specifically designed pavement and materials and structures, collect additional data, and to see whether this type of data be consistent with this performance, or what type of changes do we need to change these hyperparameters or the architecture of the design, right? But the module there, I think the framework is it should be applicable. It's just material properties are different. Environmental conditions changing, right? Climate changing, the temperature maybe and the humidity and everything has a bigger change, in the recent years, right? I think that's truly, very good question. I told Jin Liu, I want to make sure I understand each of the step, and you did, and Fang Yu as well, right? Because I'm going to go to UIUC, that group, you have all of talent people in there. They are very strong. I don't want to disgrace myself and disgrace my friend, Imam, right? So I want to show, you ask a question, I can address that question, right? Because otherwise I feel a little bit distressed, right? Disgraced, all right? Yeah, and I think strongly that's a really very good question. You can say that, with that question, in a sense, first also your question, in a sense, that's the open opportunity. Open the opportunity of how the DOT, like maybe a state DOT or national, how can we make a change for our future? We use this, AI-based or material genomic. That's the approach for design a better, mixes, right? And this design is performance together, right? Mix design and performance together. Remember that time sequence will predict the future performance, right? Very good question. I love to, to discuss with you. And open, remember, inspired me, trust me, right? But that question really inspired me, but I don't think I would be able to get that one going and put the pressure on Imam, right, to get this going on. Yeah. Any other questions? Yeah.
Quick question.
Yeah.
Quick question for Professor Wang. So I think it's time for us. Thank you, Professor, for giving us this nice presentation. Let's